All right, so we have an experiment here called the Muon experiment. In 1940, Rossi and Hall basically set up a lab in Echo Lake and in Denver, Colorado. What they did is they were looking at muon. So a muon is a subatomic particle. The symbol for it is a mu, generally plus or minus. Sorry, that's a nu. A mu plus or a mu minus. They have both of them. And what happens is, as these are particles that are created in outer space, they enter into our atmosphere and they can decay. And you can get an electron plus a neutrino, an electron anti-electron neutrino plus a muon neutrino. That's just sort of side notes right there. But these muons are coming in and they will decay. And so you count the number of muons up here, you count the number of muons down here, and you just do a comparison. So the muons, as they're coming in, at that point, they're probably using cloud chambers. So you have a box here with superheated liquids, and superheated liquids are liquids that are ready to boil, but you have so much pressure on them that it keeps them from boiling. But the slightest disturbance will suddenly get them to start to boil locally. And so what you end up with is a bubble here, and this bubble will expand, and so you can see the direction they're going in by the direction of the decreasing size of the bubbles. So you have a particle going that way. Now, the mass of a muon is about 207 times the mass of an electron. And I put a little electron right there. And the average lifetime, so the mean life, or average lifetime, is 2.196981 times 10 to the negative 6 seconds. That's a microsecond. So that's the average lifetime. The speed that they were traveling was 0.994 times the speed of light. And so if that's v, that means beta is 0.994. which means gamma is 1 over 1 square root of 1 minus 0.994 squared. And so we can work through that math. 0.994 squared, 1 plus square root. And this becomes 9.1424. Again, it is unitless. The number of muons they counted up here was 568. All right, so let's take a look at this experiment from 2 points of view. Let's first assume no time dilation. In other words, classical physics, time is the same everywhere. So if we do that, figure out the distance that they actually have to travel here, and I guess I left that part off. This distance right here, this is about 1,900 meters. Now, it wasn't set up directly like this. These were somewhat separate, but figure the number of neutrinos at this level is the same. Number of neutrinos at this level would be the same. So as any other point at that same level. So 1,900 meters. So the question is how long does it take for this muon to travel the 1,900 meters? Well, I know that distance is equal to speed times time. And so the distance is 1,900 meters divided by the speed, which is 0.994 times the speed of light. We'll just round off that one. 10 to the 8th meters per second. For those who missed it, time is equal to distance over speed. Distance over speed. So we have 1,900, 0.994, and then 3 times 10 to the 8th. And what we end up with is 6.37 times 10 to the negative 6 seconds. So it doesn't take very long. Now to figure how many neutrinos, we have something that has a half-life. We have the number of neutrinos. This goes back to math class. I'm not quite sure which one you do this in. This might be pre-cal. Is equal to n sub naught e to the negative t over tau. That's it, right? That's a mean life. That's not half-life. All right, so we have 568 is the number we started with. times e to the negative 6.37 microseconds divided by the mean life, which is 2.197 microseconds. These units will cancel, fortunately, because exponents raised to a unit in an exponent really messes things up. So 2.197 e6 negative divided by, make that negative. I want e raised to that, so that's e raised to that, and then 568 times. So what we would expect is 31.25. Obviously, you aren't going to get a fractional muon. So 32 muons down in Denver. And I'm obviously pointing off screen there. So now, that's the prediction here. So now assume time dilation. So if we're assuming time dilation, that means that the time in the muon's reference frame is different than the time in our reference frame. So gamma TP is equal to time here. I want to figure out how much time elapses according to the muon. So gamma we already calculated. That's 9.1424 times the proper time is equal to the amount of time it takes in our space, which is, I just calculated that, 6.37 microseconds. And so in the muon's reference frame, it's not aging as much, so I take the 6.37, 9.1424 divide, and I get 0.697 microseconds. In other words, what we're saying is, even though that's the amount of time that passed on Earth, that's the amount of time that passed for the muon. Well, if the muons are living and dying by this time right here, well, our prediction would be n is equal to n sub naught e to the negative t over tau, which is 568 times e to the negative 0.697 divided by 2.197. And so we take 2.197 divided by the negative exponent, and then e raised to it, and then 568 times. And we have a prediction of 414 muons. So we have a very clear difference in predictions here. One's predicting 414, the other one's predicting 31. And the actual number that was detected at the bottom, 412. This clearly has some credence here. There's something to this, and this all stems back to that light travels at a constant speed regardless of the reference frame. And so that is the difference between the two, and that's the muon experiment.